Assalamu alaikum and welcome to lecture number 11 of the course Digital Signal Processing. In this lecture we are going to discuss about the Z transform, properties of the region of convergence, and then properties of the Z transform. So from the examples we have considered so far, you understand that the mathematical expression alone is not sufficient to uniquely describe the signal. We also need the ROC, or region of convergence. So the example so far we have done, we can reduce the following properties of the region of convergence. The first one is that region of convergence, or ROC, depends on whether a signal is a finite or infinite duration. Also whether the signal is causal or non-causal, or it is two-sided, that it contains it is from both sides, that is negative and positive side of the axis. So a finite duration signal has a Z transform with a ROC that includes the entire Z plane except possibly the points where Z equals to 0 or the points where Z equals to infinity. The right-sided sequence or causal infinite durations sequence or signal has a Z transform that has region of convergence exterior of the circle, that is absolute of Z is greater than A. Similarly, for the left-sided sequence, or we also call it anti-causal sequence, for the infinite duration case, the Z transform has a ROC, that is the interior of a circle. So Z absolute is less than A. Similarly, a two-sided sequence, or double-sided sequence which is of infinite duration, has a Z transform with a region of convergence, that is annular region or ring or donut shape, right? So in that case, Z absolute is greater than A and it is less than beta. So I hope this is pretty straightforward to you, because based on the examples you have done, because for all these cases we have done numerical examples, and by looking at those examples you can easily verify these properties. Poles and zeros. So by definition, zeros of a Z transform x of Z are the values of Z for which x of Z equals to 0. So they are called zeros, right? Zeros are the values of Z for which x of Z becomes zeros, whereas poles of x of Z are those values of Z for which the Z transform blows up. That means it diverges and x of Z becomes infinity. So we represent x of Z graphically by a pole zero plot in the complex Z plane. Poles are indicated by crosses, whereas zeros are indicated by the circles. The Z transform of most signals of interest is a polynomial for finite duration signals, or rational function for infinite duration signals. You have done examples for the both finite and infinite duration signals. To find poles and zeros of the Z transform, express x of Z in positive power of Z, right? Then determine the roots of the numerator and denominator polynomials to get zeros and poles respectively, right? That means the roots of denominator polynomial will give you poles, whereas roots of the numerator polynomial will give you the zeros. And you understand why the ROC of Z transform should not contain any poles, right? So for causal or right-sided infinite duration signals, the ROC is the exterior of the outermost pole, whereas for anti-causal signals, anti-causal infinite duration signals, the ROC is interior of the innermost pole, right? So let's have an example. All those, although you have done these examples while doing the Z transform, so let's now consider them for finding the pole zeros. So the first example we did, it was the a of n, x of n, right? This is your x of n, that is equal to a to the power n u of n, and you find its Z transform, and you know its Z transform results into 1 over 1 minus a z inverse, or it can also be written as z over z minus a, right? And the ROC for this one was z absolute should be greater than the a absolute. So to find the value of pole zeros here, okay, so that's x of z, and you know what is zero? Zeros are the roots of the numerator polynomial. So numerator here is z, so values where z equals to 0 are the zeros, right? So this is the complex plane, right? So on the x-axis we have real, and on the y-axis we have the imaginary part. Okay, now for this signal, if we assume that a is less than 1, okay, for example, if a is between 0 and 1, so that means it's something like here. So you see what is the, that's your 0, right? Zeros, we have only 1 0 here, so the location of the 0 is at z equals to 0. Okay, and how many poles we have? So we have only one pole, and the location of the pole is, you know, by definition, the roots of the denominator polynomial, right? So that means the point where z minus a equals to 0, so that is the point where z equals to a. When z equals to a, this will result into 0, and this divided by 0 will result into infinity, right? That's the definition of the pole. Okay, so we have pole. For example, we just assume that the value of a is between 0 and 1, so let's this one. So you understand that we represent the pole by a cross, so I will write just cross here, which is already written here, and we have 0 at 0, right? Only 1 0 at 0, so we just mark it here. Okay, so the region of convergence for this will be the values, right, where z absolute is greater than a absolute, so that means outside this, right? So that's the exterior of the circle, that as we discussed on the previous slide. So that's the right, so that's the innermost pole, this one. Okay, so the region of convergence will be all values where z is greater than a. So this is, these are the all values outside this, right? Again, we take another example. We just did another example. If you remember, x of n was equal to minus a, and u of minus n minus 1, right? So that was another example, and you can see that this is basically left-sided sequence, right? Similarly, this one was the right-sided sequence, so the region of convergence is outside the outermost pole. Okay, now if you find the Z transform of this one, so again Z transform of this one results into z over z minus a. So if you look at the two, although in time domain both signal have different both are different, right? One is right-sided sequence and the other is a left-sided sequence, but when we find the expression of the Z transform for both of these results into the same. Okay, so but if you look at the unique thing is that is its region of convergence is inside the interior inside of the, so the pole zero diagram for both of these signals will be same, right? Location of the pole, okay, because in this case we have 1 0 at 0 and one pole at this particular location. Again, for the second case we have 1 0, right, and one pole at exactly same. But if you look at the one, because this is the right-sided sequence, so for the right-sided sequence we have region of convergence, that is outside the outermost pole, that is this one, right? So if you look at the expression for the region of convergence, so we have region of convergence has expression like this. Similarly, for this one, the region of convergence is absolute of z should be less than absolute of a, so that's absolute of a, so this is inward. So I hope this gives you some idea. Very thickly populated slide, but we'll go quickly through it. So I hope that's quite straightforward things, that rational Z transform, right? So we can represent the rational function of the form x of z equals to b of z over a of z. So for example, for k running from 0 up to m for the numerator, and for denominator we have k running from 0 up to n, and it has coefficients ak, and that's as bk z power minus k. So if we expand it, we can write it b0 plus b1 z minus 1 and so on up to z power minus m, and similarly this one can also be expanded to this one, right? So b of z is the numerator polynomial, and z inverse of degree m, you understand m is the highest power, right, or the upper limit, and a of z is the numerator. And so the z transform expressed here can be alternatively expressed in positive power of z by factoring out b naught z power minus m from the numerator, and a naught z power n from denominator, so that we have positive powers of the z. Okay, so I hope that's quite straightforward. Or so by taking b naught z power n common, we b naught z power minus m common, right? So then we have here it was b naught, so it's taken common, so we are left with z power m plus b1 over b naught z power m minus 1 and up to b of m over b naught. Similarly, taking a naught z power minus n common, so here we had a naught, so when you take this common, so we are left with 1, and because you are also taking z power minus n common, so you multiply a power, z power plus n, right? So similarly, z power n plus a naught over a1 over a naught z power minus n, and so on. And remember that b naught and a naught, they are not equal to 0. Okay, so then by factoring the numerator and denominator polynomial, we can easily obtain x of z equals to, because you see this one is divided here, it has power of z power minus 1, so if I move it upside, the power will be inverted and it will become n, so it will become z power n minus m. And so we have b naught or a naught z power n minus m, right? And that we have z minus z1 into z minus z2 up to z minus zm, and again we have for the zeros also, so z minus p1, z minus 2, p2, right, up to z minus Pn. So let denote B naught by A naught by G. So we say, okay, G Z of n minus m, and we can write them in the product form like this, right? Okay, so we get this expression by factoring the numerator and denominator polynomials. So we get g of g into z of n, z power n minus m, and this one. So again, we have how many z's here, how many terms here? So we have basically m terms, right? So if I take z common from each of the term, so what I get here is 1 minus z1, because we already have z1, and we take the z common, so we'll multiply with z power minus n. Okay, again for this one, I hope that's clear, or let me write it. Or let's simply ignoring this one, and we just have this expression, right? That these are the factored numerator and denominator polynomials. If I take z common from all these terms, right? So how many terms are these? These are up to z, right? Up to m. So that means z common here, again from the second, from the third, up to m. So that means I take z power plus m common, right? So what I'm left with is, let me write. So okay, we can express it like this, and okay, so again just I'm taking z common, right? So how many terms are there? There are m terms. So if I take z times right, m times z, so that will become z power m, which I have written here, right? So what will be inside? So I take z common for, so here I'll be left with 1, and because there is no z here, so it will be z1 divided by z. So we can also write it z1 times z power minus 1, which I have written here, right? So these z1, z2, these are all zeros. Okay, and similarly for the denominator term, we can take z common. So how many terms are there? There are n terms, so z power n is taken common here. So I'm left with here 1 minus p1 z inverse, 1 minus p2 z, and so on, right? So you understand. So now this z power n, okay, cancels with this one. Okay, similarly z power plus m and z power minus, both are multiplied, power are added, so it will result into 0. So anything power 0 will be 1. So we are just left with this term. Okay, and let me represent it by g as described here. So we can write it g into 1 minus z1, right? Z1 is 0. These are basically zeros. Okay, z1, z2, z3 up to z m, because this term consists of m zeros, and similarly we have these n poles. Okay, so we can write it in the general, because they are multiplied. So in the product form we can write g and product k running from 1 up to m, 1 minus z k z inverse, and again here product k running from 1 up to n, 1 minus pk z inverse, right? So where zk, the roots of numerator polynomial bz, right, az, right, for right. So zk's are the roots of numerator. Okay, and right, so if you look at the expression here, so basically bz's are the numerator. So zk, the roots of numerator bz are the zeros, right? So because by definition you understand what is 0, and similarly pk, the roots of denominator which is represented as az here, so are the poles of x of z, right? So zk and pk are respectively zeros and poles of this x of Z. Whereas G, which is equal to B naught or A naught, is called the gain term, right? So the expression in the 7 are the referred to as pole zero form of x of z, right? And each term in the numerator, right, these, they contribute 1 0, and similarly each term and denominator contribute to poles. So we can say that for example, this is your any 0, okay? So 1 minus zk, z inverse, so we can write it like this. So that means each term in the numerator contributes to, because you see that it has 1 0, okay, 1 z equals to zk, and it has one pole when z equals to 0. Right? So that means this contributes 1 0, and the 0 is when z equals to z of k, and one pole when z equals to 0. So that means it contributes 1 0 and one pole, right? The pole will always be at origin. So similarly, each term in the denominator contributes one pole and 1 0, right? So 0 will be at the origin, and the pole will be at the location where z equals to pk, right? Now there's another question. If we don't have same degree, right, that is denominator and numerator, they have different degrees. So the case one is if the denominator, which represents the number of poles, have value greater than the number of zeros, right, then we say there are n minus m zeros at the origin, right? Similarly, if the numerator has higher degree than the denominator, then we say that there are n minus m poles at the origin. Okay, as a 0 exists at z equals to infinity if x of infinity equals to 0. Similarly, a pole exists at z equals to infinity if x of infinity equals to infinity. So the number of poles is equal to the number of zeros in x of z, and these include the one that are at the origin and infinity. Okay. So your homework is to determine poles and zeros for the Z transform obtained in example 1, 2, 3, 4 of the Oppenheim book. You understand that's your book which we used in this course, right? The discrete time signal processing by Alan V. Oppenheim and Ronald W. Sheffer. So that's our book which we follow for this course. So you go to the examples as mentioned here and find. Okay. One more thing important, that is, if we are given a pole zero diagram, we can determine the Z transform from the pole 0 up to the scaling factor, because there was scaling B naught or A naught. So as an example, consider the pole 0 diagram below, for which the Z transform can be determined as follows, right? So we are given, we have two zeros, 1 0 at 0 and 1 0 at minus 1 by 2, and it also consists of two poles, one pole at 1 by 2 and one pole at 1. So given this, so this is within the scaling factor, right, not the exact, because you see that for we had expression for the scaling that was b naught or a naught. So let we say b naught equals to, for example, 4 and a naught equals to 2. So that means we will it will be simplified to 2. That means we cannot have exact scaling. So I hope you can do it. The topic is the properties of the Z transform. The Z transform holds the following property, which can be easily verified. So the first property we are going to discuss is the linearity. You understand what is linearity to test whether some transformation or system is linear or non-linear. It has to hold two properties, that is scaling and superposition. So the two properties are scaling and the superposition. So superposition is if x1 of n produces, or the Z transform of this one is x1 of z, and x2 of n has Z transform x2 of z, then adding the two, okay, so if I take the Z transform of x1 of n plus x2 of n, it will result into x1 of z plus x2 of z, which is the superposition, the adding input, right, or the addition of the input. Similarly, scaling is that if x1 of n produces x1 of z, that means if I scale it by a factor of whatever factor, for example by a factor of a, then the transform should also be scaled by the same factor. So we can combine the two properties, that is scaling and the superposition. So if I have x of n such that it is the scaled version of x1 of n and plus scaled version of x2 of n, where both x1 of n and x2 of n have scaling factors of a1 and a2 respectively, we add them and then we apply the Z transform on this whole. So it should produce x of z such that x of z consists of a1 x1 of z plus a2 times x2 of z. So if you look at the original equation, you can say that because the x1 is scaled by a factor of a1, so its transform, which is x1 of z, is also scaled by a factor of a1, and similar argument apply for the x2 of n. The important thing is that the expression will be this one. And now we come to the ROC, because you understand the mathematical expression alone is not enough for the complete description of the signal or the response of the system. We also need the ROC. So how about the ROC? So the ROC of the resulting signal will be the intersection of the ROCs of the individual signals, right? So like here x1 of n has ROC, right? It's for Z transform is x1 of z, and it has the ROC equals to R1, and this one has R2. So the overall ROC of x of n, which is the which is composed of the scaled version of x1 of n plus scaled version of x2 of n, it will consist of, or it will have the ROC, the intersection of the individual ROCs. Okay, the second property of the Z transform we are going to discuss is the time shifting. So you understand the time shifting, that a signal in time domain is shifted by a factor of k if we have y of n equals to x of n minus k, right? So if the k is positive, then we say it's the delayed version of the input signal, that is the y. For example, we say that y of n is the output and x of n is the input, then we say y of n will be delayed version of x of n by a factor of k if k is positive. Or if k is negative, then we say y of n is basically advanced version of x of n by a factor of k, right? So k should be positive for the shift right and negative for the shift left, which shift right is also called delayed and shift left is also called the advanced version of the original signal. Okay, so for example, x of n has Z transform of x of z, then the shifted version of x of n represented by y of n, and which is equal to x of n minus k, and the shift is by amount of k. So if we take the Fourier transform of this one, then the Fourier transform, it's just simply multiplication by a factor of z power minus k. If you recall the Fourier transform, so we had similar expression for the Fourier transform as well. Then again comes the question, what will be the ROC, or what effect it will have on the ROC of the original signal, right? So the resulting signal will have ROC which is equal to the ROC of the original signal, except for the possible addition or deletion of z equals to 0 or z equals to infinity, right? So I hope these two properties you are very familiar with these, so they are quite straightforward. The third property we are going to talk about is the time reversal. So you understand what is time reversal. Time reversal is just the reflected version of the original signal about the vertical or time axis. So if a signal, generalized signal x of n, it has Fourier z transform of x of z with ROC equals to r of x, right? Then its reflected version, which is represented by y of n, and we can say we can write y of n equals to x of minus n. If we take its z transform, then y of z will be equal to x z of inverse, right? Reciprocal of the z. So it will be reciprocal in the z domain when you reflect the signal in the time domain. So its ROC will be also the reciprocal of the ROC of the original signal, which is r of x, right? So the reflection in time domain corresponds to inversion in the z domain, and we obtain y of z and its ROC by replacing z by z power minus 1. So if you have r of x has, for example, a value, right? The ROC of the original signal is, for example, z absolute, that is greater than alpha and less than beta. Then in that case, the ROC of the y will be inverted or reciprocal of r of x. So that means z absolute for this case will be equal to greater than 1 by beta and less than 1 by alpha. You understand, because beta is greater, so if we take reciprocal, it will have smaller value than the reciprocal of alpha, right? The fourth property we are going to discuss is the scaling and z domain. So we have a signal x of n, it has z transform represented by x of z, and it has ROC which is represented by which has value of r of x. Then y of n, which is equal to a of n to the into x of n. So that's basically scaling and z domain, right? So in z domain, if you multiply a signal by exponential in time domain, in z domain it's equal to replacing z by a, replacing z by a. That means you actually scale it in z domain. So the ROC for the resulting signal will have value equals to the ROC of the original signal times the absolute value of the a, the exponential signal base, right? So here a can be a complex constant. It shows that scaling in the z domain corresponds to multiplication by an exponential in the time domain, right? So in z domain, if we scale, in time domain it corresponds to multiplying by an exponential signal. So that's why the heading is scaling in z domain. Okay. Also, y of z and its ROC are obtained by replacing z by a. In particular, if r of x is given by this value, that is z absolute is greater than r1 and it's less than r2, then the value for the reciprocal not reciprocal signal, the scaled signal will have ROC represented by R of y, and it will be equal to Z absolute greater than alpha times R1 2, right? So that means we are just multiplying the limits of the ROC by the factor of A absolute. I hope this gives you idea. Before proceeding to the next property, let's have some examples on the properties we have discussed so far. So here in this problem we are given x of n such that x of n equals to cos omega naught n times u of, and you understand what does u of n means, right? So u of n is a step signal, and it is only one when its argument is equal to or greater than 0. So that means for the negative values of its argument, which is now n, it will be 0. So this signal only exists from 0 up to infinity, right? So for the negative values of the n, it doesn't exist. Now to find the Fourier transform, Z transform of this signal, that's quite straightforward because we have studied about the linearity, so we can express it, and then using the Euler equation, so we can split it into two complex exponential signals. So we know cos omega naught n equals to e power j omega naught n plus e power minus j omega naught n divided by 2. So we can expresses as two signals, so one this exponential, one this one, and u of n multiply with both of them. So that means we can represent it like this. So that means x1 of n basically equals to e power j omega naught n u of n, and x2 of n equals to this one. So hope this gives you idea. I think you can do it by yourself. So you just take the Z transform of this one, then Z transform of this one, then if I sum these, so the sum of the Z transform will be equal to the individual Z transforms, right, summation of the individual Z transform, and because we also have scaling factor of 1 by 2, so the individual Z transform will also be scaled by a factor of 1 by 2, and this way we can get the expression for the Z transform. Also, when we talk about the ROC, so you understand this should be greater than 1, right? So product of this one, so that means Z absolute equals to absolute of this thing, which is equal to 1. So that means that absolute, whether for the negative exponential or for the positive exponential, the absolute value of both is equal to 1. So that means for the ROC, Z absolute should be greater than 1. So you must do it by yourself, although it's quite straightforward, and I think you shouldn't have any issue with it. So if you have any issue, we can discuss it in the class. So that's the overall result for the previous example. Again, we have another example of x of n equals to u of minus n. So you understand, you have just studied about the time reflection, right, or the time reversal property. So because you know the Fourier Z transform of u of n equals to this one, so you can easily find the Z transform for the reciprocal system using the time reversal or time reflection property. Okay, so the next property is differentiation in Z domain. So x of n has Z transform equals to x of z, and it has the corresponding region of convergence that is represented by r of x, then y of n, right, equals to n times x of n. And basically this how you get this one is basically you have x of z, and we represent its derivative by y of z, so we say y of z equals to derivative of x of z. So if you take the derivative of this one in the Z domain, then it's equals to derivative of this will equal to multiplication by minus z and d of x upon d of z, right? So the differentiation doesn't affect the ROC, so the ROC of the resulting signal will have ROC equal to the original signal, right? That means the y of z will have the same ROC as the x of z. So that means differentiation in z domain corresponds to multiplication by the independent variable, which is n, in the time domain. The next property is the conjugation for the complex signals. So if x of n has Fourier z transform of x of z with the ROC R of x, then the conjugate of this signal represented by x static, you understand, we represent the conjugate. So you understand when we take the conjugate of any complex number, then the sign for the imaginary part changes, right? So if we take conjugate in time domain, then it corresponds to the conjugate of the signals into the conjugate of the z. And in this case also the ROC doesn't change. Okay, the next property is convolution property. So you understand, like you have done the about the Fourier transform, that multiplication in time domain, right? Because in the previous lecture we talked about the discrete time Fourier transform, right? So there also we discussed about the convolution property, and again it's a similar. So convolution in time domain corresponds to multiplication in the z domain. So for example, x of 1 has Fourier z transform x1 of z, and x2 has Fourier z transform x2 of z, and this one has ROC equals to R1, and this one ROC equals to R2. Then convolution in time domain corresponds to multiplication and in z domain, okay, or z domain, or right? And the ROC of the resulting signal will be the intersection of the ROCs of the individual signals, right? It's very powerful because it converts the convolution of two signals, usually a complex exponential, usually a complex operation, right? You understand multiplication versus the convolution. So you understand convolution is very complex process that it takes I mean, if you do it automatically using the computer, still it requires a lot of computation, whereas the operation of multiplication is quite straightforward. So definitely all of us go for the simpler things, so we'll prefer the multiplication over the convolution. So if you you have to find the convolution, then straightforward method is you take the z transform, then multiply both the signals, right? And then take the inverse z transform, and you get the answer, right? So again, keep in mind that this will be the multiplication, but the ROCs of the resulting signal will be the intersection of the ROC of the individual signal. So we end the lecture here, and as a homework I give you this numerical problem. Here you have to find the convolution of these two signals, and you understand that's quite straightforward, that instead of taking the convolution, why not we go for the multiplication. And how can we move, or how can we go for the multiplication? We can take the Fourier z transform of both of the signals, and then once we have the z transform, we can just multiply the two signals there, and then the ROC of the resulting signal will be the intersection of the two ROCs, and then we take the inverse z transform to find the answer. Okay, so that's all for today. If you have any question, you can ask me. Remember that in this course we are using the Discrete Time Signal and System Processing book written by Alan V. Bonham and I. Ronald W. Shepard. Okay, so that's the book that we are following, and most of the contents, they are from this book. Okay, so see you. Allah Hafiz.